Hey everybody, welcome to the module 3, topic 3, review. This is the last topic of the module. So we're going to head to module 4, which is kind of completely new stuff, trig. But first we have logs to deal with in the form of what I'm calling a mini test because it's shorter, it's mini relative to the other tests. There's still some stuff on it. But hopefully, as you can see by just the review and hopefully the length of this video, I haven't recorded it, so I don't know exactly, but I hope it's a little bit shorter. Feels like it's a mini assessment, okay? So here's what you're gonna need. You're gonna need your review sheet, as well as a calculator that can do logs, okay, and logs of different bases. The TI-84 works, so that's what I'm gonna use. I'll teach you the shortcut to how to get to different base logs. You can also just use Desmos. And if you're typing on a keyboard, you can hit shift underscore to make a subscript to change the base of the log, or in the little funct, F-U-N-C on Desmos, there's one you can choose that has log and then it has this little like circle, or I think it's log base A maybe. And you can use that one to change the base of log because we're going to be doing that quite a bit, okay? And then I also know, on top of a calculator, that you guys need something a little bit extra to keep you focused. So we'll just go ahead and have this going for you while we get into question 1 and 2 of the review. All right, so to start out, we are asked to convert from exponential and log forms. Okay, so this one is a log form. We want to convert this so that it looks something like this one. And then vice versa, when we get to this problem, we want to convert this so that has a log in it. Okay, so we need to write this so it has an exponent, this so it has a log. And the way that I sort of think about this is the loop-de-loop. Wow, that X was bad. Okay, and what I mean by that is, if you start at the base, so the base of the log, you have to work your way around the problem to convert from log to exponential form. So here's how we do it. We say this base to the power of 3 is equal to x. So equals x, okay? So how that's written is 4 to the power of 3 equals x, right? 4 to the power of 3 equals x, which means that x equals, to answer this question, I'll just have the calculator do it, 4 to the 3 is 64. All right, so that means that x equals 64. Boom, done. All right. Next, we're going to go the other way, which I like to think about these colors, right? So I can look and I can see that 3 is the base. So I know that that is going to be the base of my log as well. So it's going to be log base 3. And then the thing that is in the argument, what it equals, is in this case 243. So log base 3 of 243 is equal to whatever your power was. So x, right? I kind of just undid the loop-de-loop. I kind of thought in my mind, well, to convert from this to this, 3 to the power x equals 243. That's what it says. And so I just need to figure out what this log is, all right? And here's how you do it on a TI-84. So you can get there, I believe, through math. If you go math and then it's one of the numbers, it's a log base. That's a lot of scrolling though. So if you don't know this shortcut, there's a shortcut to a shortcut. Are you ready? So I'm going to get out of it. If you're just on any screen, you hit alpha. Okay, so the green button, alpha. Swoop. And then you hit window. Alpha window, and then if you look, it's number 5 right here, so 5. So your code is alpha, the green button, into window. That's not how you spell window. Window. It's like the skinny one at the top, and then you press the 5 key. And it'll take you to log base, which allows you to type in anything you want for the base, which in this case is 3, and then our argument is 243, which is equals 5. So 3 to the power 5 equals 243. So x equals 5. All right, cool. Let me move, actually. Let me scrunch this all up. There we go. There we go. So alpha window 5 gets you to log base. All right, cool. That's as easy as the first two. Next up, this one's properties of exponents and logs, combining basically like terms. Let's start with the exponent one. Okay, so there's a couple things we need to remember. Number one is that when you have like bases being multiplied, so like x squared times x cubed, this combines to x to the 5th. So we add, right? With like bases, we add. And the reason for that is this is basically x times x times x times x times x, which means in total, this is x to the 5th, all right? So we can use this logic to help us out here. So let me simplify the top. I'm gonna sort of think about each of my different terms. So I have x's in here, I have y's in here, and then I just have regular old numbers, so a 2, all right? So when I go to rewrite the top of this equation, or sorry, this expression, it's gonna be a 2 out in front because the 2 can't combine with anything. There's no other numbers, there's no other regular numbers. Sorry, I didn't do these ones as well. But the x's are gonna be x to the -1 times x to the 4th. Well, even though it's a negative power, remember that flips it and puts it on the denominator, but because I'm multiplying them, I can just add. And so in total, that's gonna be x to the 3, right? -1 plus 4 times y cubed times y, all right? Now you gotta remember, if it's just y, then it's implied that it's to the 1st power, which means that the top is gonna be 3 plus 1, which is 4. So there's the top of your fraction, all right? Divided by, and here's another rule, okay? So the next rule we need to know is the power to a power rule. So here's an example. If I had x to the power 2 cubed, all right? A lot of people get these two confused, right? They're gonna say that these two are the same thing, but they're not. When you have a power to a power, you multiply. And here's why. This is basically x squared times x squared times x squared, right? It's x squared cubed. So it's x squared times x squared times x squared. Well, in total, that's x to the 6th. And so when we have a power to a power, we multiply, all right? We multiply our exponents. So when I look at the bottom, I have sort of a similar thing going on where these 3 different terms are being raised to the 3rd power. And so I have to think about it like that. I kind of distribute this exponent in. So first we start with 2 to the 3, right? We have to also apply the 3 to the 2, and that becomes, well, I'll just write it as 2 to the 3 for now. We can get a little more simple in a sec. And then x to the -3 to the power 3. Well, you just multiply the exponents. So it's going to be x to the -9, all right? And then y squared cubed, well, we just saw that's going to be y to the 6th, all right? Well, let's try and simplify this as much as we can. I know that this will essentially cancel, right? The 2 here and then 2 cubed and make this 2 squared, all right? So I know that on the bottom of my fraction, I'm going to have a 4, that's 2 squared. And then my x's are kind of going to cancel, but not really. Since this is a negative exponent, when you divide, you subtract, right? So opposite of when you multiply, you add. When you divide like bases, you subtract, which basically means I'm going to take 3 minus -9, which is 3 plus 9. And so on the top, I'm going to have x to the 12 because that's 3 plus 9. And then in this case, y to the 4th and y to the 6th, well, all 4 of these are going to get canceled, and that's going to cancel with 4 of these on the bottom and leave us with just y squared. And that's as simple as we can go. All right. Boom, there we go. We leave the y squared on the bottom just because the y squared is on the bottom here, and then the 4 was on the bottom as well. I like that. You could also write these as negative powers if you'd like, but I won't. I'll just leave it like this. All right, so on the other hand, we have log rules as well, which allows us to combine like terms in terms of log or anything that has a similar log with a base, okay? The first thing that we need to apply is the exponent rule, or the power rule of logs, which says if you have a number that's multiplying a log, that's the same as if that thing that's multiplying, so in this case 4, was an exponent inside the argument. All right. So one way to rewrite this is log base 2 of a to the 4th, right? I can bring this 4 into the exponent. And same thing here. This is log base 2 of b to the 7th. Okay, so that's the power rule. Oftentimes you have to go reverse. Oftentimes the exponent will be here and you want to put it out in front. But in this case, I'm asking you to condense. So, do the opposite. All right, and then the other rule we need to know is the log multiplication, right? It's the top one, I believe, on your sheet with the columns. And it's that when we add two logs together, if they have the same base, well, that's the same as if I multiplied the arguments together. So this whole thing is the same as log base 2 of a to the 4th times b to the 7th, right? If there's two things being multiplied in my argument, you can split them up by adding the logs, or you can go the other way and combine them by multiplying, right? It's kind of like here, we add our exponents when we multiply, well, we add our logs when we multiply, right, inside the argument. But this is the answer, right? This is condensed into a single logarithm, so it's good. All right, moving on to 5 and 6. 5 is super similar, except this time we are dividing, all right? We're going to divide inside the log, which, just like in this problem where when you divide, you subtract, you also subtract the logs. So it'll become this. Log base 6, because the log base 6 is here, of u squared minus log base 6 of v squared, all right? I used the division rule of logs. I don't know if it's called the quotient rule or division rule of log. The way that I remember this, and maybe this is weird and I don't know if it's good for you or not, is when I divide inside a log, it looks like a minus sign. And so that's how I remember to subtract them. All right. Now there's one more thing I can do, which is kind of undoing these exponents. I have an argument with two exponents in there, right? It's to the power 2, which means I can bring this out in front. So this is the same as 2 times the log base 6 of u minus 2 times the log base 6 of v. Log base 6 of v. All right, there we go. All right. Number 6, evaluate the logs using a calculator. This is a test that you know how to use the calculator or Desmos, right? So once again, the keystroke is alpha window. All right, so that's alpha window and then 5. That's how I get to it. And so if I want to find this one, log base 6 of 42, that's 2.086. 2.086. Nice. ln is a special type of log. It's the natural log, or in French, the log naturel. That's why it's ln. I don't know if that's a joke. I don't know if that's real. I think that's a joke. But it's a button on your calculator. It's log base e, right? Technically, it's log base e of 5, but they changed it because they didn't want to say loge. That's not true either. I just made it up. But natural log is just ln. It's not an I, by the way. It's an L. And then you just type 5, and you get 1.609. 1.609. All right. And then this one, I will type into a calculator, but you hopefully won't need it because there's a rule about this. The base equals argument rule. It's on your sheet, your review or your logarithm rule sheet with the backside as exponent rules. This is going to be 1 because 2 to the power 1 equals 2. But here's the calculator to prove it. So alpha window 5, log base 2 of 2 equals 1. And in fact, that's how we solve all these logs. When the base of the log is the same as the argument, it essentially cancels, right? It just equals 1. All right, 7 and 8. And this is what we're going to do to both sides to try and solve these problems, okay? Number 7 is kind of tricky, so let's see if we can work our way through it. They say solve the exponential equation by rewriting both sides of the equation with the same base, all right? With the same base. The reason why we want the same base on both sides is because then we can take the log with the base of that thing, right? Of that base, which will then cancel everything and leave us with just the exponents, right? So this looks like one on the packet. If you did the packet, the front page, and we essentially need to rewrite both of these so that they are in terms of something that can be raised to a power, all right? So here's what I'm going to think about. First of all, I want to find if 25 to the power of 2 is 625, and it is, okay? So that's not a coincidence. The reason why I wanted to say that is because if I can turn this 625 into a 25, then I can solve this problem super easily. And that's what I'm going to do, all right? So currently, we have 625 to the power of 2x minus 2. However, I just saw from my calculator that 25 to the power 2 is equal to 625, which means 25 to the power 2 to the power of 2x minus 2 is equal to 25 to the power of negative x minus 2, right? I basically just said 625 is equal to 25 squared. The reason to do that is because I can now use a power rule, the power to a power rule, and say that when I'm raising this 2 to the power of 2x minus 2, I can just multiply these to combine. And so this just becomes 25 to the power of 2 times 2x minus 2 equals 25 to the power of negative x minus 2. Negative x minus 2. And now what I'm going to do to solve for x is I need to cancel these bases. And essentially, all I have to do is say, well, I'm going to take the log base 25 of both sides. Let me move this equals sign over here. Equals the log base 25 of this. And as we saw from the last page, when you take the log where the base is equal to the argument, well, those cancel out. And because these things are in my exponents, I can actually bring them in front of the log. And so essentially all I'm left with is these are gone, these are gone. These get, because of the power rule, the exponent inside the argument rule, these just become what's left over. So 2 times 2x minus 2 equals negative x minus 2. And now we're just doing algebra, right? This is now just an algebra 1 problem. I'm going to distribute. So I get 4x minus 4 equals a negative x minus 2. And now I just need to solve for x. So I want to get all my x's on one side, all my numbers on the other. So I'll start by adding x to both sides. And while I'm at it, since I want to move this negative 4 over here, I'll also add 4 to both sides. That way the x's get canceled from this side, the 4's get canceled from this side. I'm left with 5x equals negative 2 plus 4 is 2. And so divide both sides by 5. X equals 2/5. Whoop. Very nice. I think I did everything right. Hopefully. I think so. That's gotta be right. All right, cool. So the difference between number 8 and number 7 is that when you try to cancel things out here, well, I need to cancel not a log anymore. Well, I kind of do. I just need to cancel this 10 somehow. But first, I want to make my life as easy as possible. So I'm going to try and get rid of anything that isn't just this 10 to the power of this, right? So I'm trying to isolate this term to start, okay? Well, what that means is I need to get rid of this minus 4 that's being subtracted. I can do that by adding 4 to both sides. I get negative 9 times 10 to the power of negative 7x minus 10 equals 75, negative 75, right? 4 more than negative 79. And then I'm going to divide by 9, negative 9 that is, because this negative 9 out front is multiplying the thing I want to isolate. So when I divide, they cancel. What's 75 divided by 9? Is that a nasty one? Why though? Why is it? Why is it? Anyway, is negative 79 plus 4 really negative 75? And then I have to divide by 9. Oh, who did this? Who made this problem? It wasn't me, but I'll accept the blame. Anyway, so those cancel, and I'm left with just 10 to the power of negative 7x minus 10 equals. Can I reduce this fraction? I guess I'll just say, I know the negatives are going to cancel, so I'll just say 75 over 9. All right. Okay, so now we're at a point where I need to get x by itself, but the problem is it's stuck up here in an exponent. And the way to do it is the same as this. Okay, so we're going to try and cancel out the base, and we're going to do that by taking the log base 10 of both sides, right? And so I'm going to take the log base 10 of the left, which will hopefully just cancel it, and it will. And that means I also have to take the log base 10 of the right. So this all cancels, and I'm left with, remember you can bring this out in front. So all I'm left with is negative 7x minus 10 equals log base 10 of 75 over 9. Okay. Well, this is a number that you can plug into the calculator, right? But just to make my life easier and save my calculator fingers, I'm going to try and just get x by itself and then type that all into a calculator. So I know that at some point I'm going to have to add 10 to both sides, because remember, I'm trying to solve for x. So I get negative 7x equals log base 10 of 75 over 9. And then this plus 10 is just separate, right? This can't go inside the log or anything. It just is out right here. And then I'm going to have to divide by negative 7 as well. And so really, all I'm left with is x equals this huge big thing, which we will then now just type into the calculator, all right? Well, what's good is that log base 10 is just log on the calculator, right? So this button right here, log, that's just log base 10. And so I can just take log of 75 over 9, okay? You get that number. And then add 10 to it. You get that number. And then divide by negative 7, and you get that number. So x equals negative 1.5601. Which is what happens when you type this whole thing into the calculator, okay? Most of this is just algebra. The only new thing we're doing is taking the log of both sides, or as we'll see in a second, we can actually put both sides under a common base. And that's kind of just another operation we have in our toolbox, right? We can multiply to both sides, add to both sides. We can now take the log of both sides, all right? However, if we need to cancel logs, like I mentioned, we can by setting both sides to a common base, all right? Oh, my Subway Surfers is restarting. Here we go. And so when I look at problem number 9, I can notice that both of these have a base of 7, all right? Well, just as the log base 7 of 7 is equal to 1, if I sort of rearrange this, I could say that 7 to the power of log base 7 of something, so like 2m, equals, well, that just cancels out, right? 7 to the power of log 7 just leaves you with whatever's in the argument. And so what I'm going to do to cancel out these logs is set both sides under a common base. In other words, I'm going to put these both in the exponent of a base of 7. So it's kind of like squaring both sides, but instead of applying an exponent, you're creating an exponent out of something you already had, right? You're setting what's equal already on the equation into the exponent. And what that does is just cancel these two out. And you're left with the arguments. 2 minus 4m is equal to negative 5m minus 10. I don't know why I did the parentheses here. You don't need them. And now this is once again just an algebra problem, right? We're just solving for m. And so I'm going to add 5m to both sides to get my m's over on the left, and then I'll subtract this 2 to get all the numbers off to the right. those cancel, these cancel. I'm left with a singular m, because it's negative 4m plus 5m equals negative 10 minus 2 is negative 12. And that's your answer. Right? This one, very similar to like this problem, is that when you have a common base, or when you have a common log base, the arguments are equal to each other, just like the exponents were equal to each other here. So we can just take the shortcut and be like 2 minus 4m has to be equal to negative 5m minus 10. It also makes sense because if these are equal to each other, then the arguments better be the same, right? All right, so like what about this one though? What about something like this, okay? And this is where it gets a little bit tricky because I want to first try and condense, right? I'm going to use a log rule here. So I notice that these two are being subtracted. Okay, these two are being subtracted. And so what I'm going to do is combine this log into one statement. Okay, and so I'm going to say that this is the same as log base 2. Since they're subtracted, I divide. So in the argument, x divided by x minus 6. That's equal to 2. Okay. Well, what I want to do now is the same thing to cancel out the log, except even though I don't have a log over here, it's still okay. I'm going to set both sides so that they have a base of 2 now, right? So I'm essentially putting everything here into the exponent. And the reason to do that is because that cancels, right? 2 to the power of log 2, well, that just leaves you with whatever's in the argument. So x divided by x minus 6 is equal to 2 to the power 2 over here is just 4, right? It's just 2 to the 2. Then, once we're here, we want to solve for x. And so I'm just going to multiply this side and this side by x minus 6, right? To cancel it from here, shoop, shoop, and leave me with x equals, distribute this, you get 4x minus 24. 4 times 6 is 24, right? 4. Oops, hold on. 4 times 6. Yeah. And now we can just solve for x. So I'll subtract 4x minus 4x, and then I get negative 5x equal, or sorry. Positive x minus 4x is negative 3x equals negative 24. Divide both sides by negative 3, and you get x equals 8. Awesome. Okay. So the two new sort of algebra tools that you have in your toolbox is taking the log of both sides and setting both sides to a common base, right? And that way, what ends up happening is you can cancel out things that have logs in them. You can figure out things that are in the exponent. And one thing, or one new application that we have for that is this problem, which is super hefty and looks long, but we did it in my class at least, the magnitude of an earthquake, which we solved by graphing in the past, right, in the last topic. But now we have the tools to solve it algebraically if we want, all right? So let me just break down what this means and what it's saying. This equation right here is the important one. It is the equation of how they measure the magnitude of an earthquake, okay? So the magnitude of an earthquake is a relative scale. So kind of like decibels of sound. It's not linear. It's, in fact, a log scale or exponential. So the larger the number gets, it's getting magnitudes, pun not intended, larger than a smaller earthquake, right? And the reason for that is because it's calculated by taking the log of this number I, which is an actual displacement of the Earth measured 100 kilometers away from the epicenter. Okay, so essentially, if an earthquake happens in LA, right, here's your earthquake. There's some seismograph location or some geological place where they're studying the Earth and the tectonic plates. LA gets shaken around. That seismograph reads, oh, the Earth was displaced 100 centimeters. And then they put that into the scale and figure out the magnitude, okay? Well, we're going to reverse engineer that. We're going to find this value of I, the intensity in centimeters, and we're going to compare it, well, in the equation is the standard earthquake intensity, which is 0.001 centimeters. Okay, so every earthquake is just measured in relation to a standard earthquake. All right, so let's figure out how to solve this. An earthquake in California measured a magnitude of 6.2 on the Richter scale. Okay, so let's set that up. M is our magnitude, and so I know in our equation it's going to be 6.2 equals the log of I, which we don't know yet, divided by this number, I sub 0, which is the standard earthquake intensity, which is 10 to the negative 4, or 0.0001, right, or 0.0001, okay? Well, we solved this graphically, right? We plugged this in, and we set it equal to 6.2, and then we found where the two lines crossed. But now we have logs on our side, so we can actually solve, okay? We can solve for I, and the way that we're going to do that is, since this log doesn't have a number here, remember it's log base 10, just regular log is always log base 10. And so what I'm going to do is set both sides under a common base, okay? So I'm going to say that both of these are going to be with a base of 10. So it's going to be 10 to the 6.2 power equals, this will all cancel, I over 0.0001. And so my equation becomes, sorry, this is just a right arrow. It'll become 10 to the power of 6.2 equals I over 0.0001. I'm then going to multiply both sides by 0.0001, and do that over here as well. And that'll get I by itself, right? And so then, in a calculator, I'll just say that I is equal to 0.0001 times 10 to the power of 6.2, like so. Which means that the intensity of this earthquake, a 6.2 magnitude earthquake, meant that the amplitude of the shaking that was happening displaced 158.49 centimeters. Okay, that's the intensity of the actual earthquake. That's how far the ground moved, or what they measured the ground moving 100 kilometers away. All right. Let's do the same thing, but for the earthquake in Japan. So it's also shaking around and stuff. This one is 7.1. Okay, that's the magnitude. And you might think, well, that's not that much bigger, 7.1 compared to 6.2. It's like an extra magnitude, whatever. But they already got to 6, so how much bigger could it be? Well, let's see. Remember, that's going to be equal to log of I divided by 0.0001. Remember, it's log base 10, and so I'm going to set both sides to a common base of 10. That's going to cancel out the log, and I'm just going to leave you with the argument. And so in a similar way, it's going to be 10 to the power of 7.1 equals I over 0.0001. I will then multiply both sides by 0.0001 times 0.0001. Those cancel from here. And then that tells me that I is equal to I equals 0 or 0.0001 times 10 to the power of 7.1, which is 1258.93, which the big question, and this is what they're asking, and I'm running out of room, I wrote too big. How many more times stronger was the earthquake in Japan? Well, it's how many times you have to multiply, or what, basically this divided by this, right? It's how many times bigger 1258 is compared to 158. And so let's find that in the calculator. So I'll take this, I'll divide it by 158.49. That means it's 7.94 times larger. So nearly 8 times larger. 7.94 times larger. That's your final answer. So essentially you're solving for I, you're solving for the actual intensity, and then you're comparing how different they are, which is kind of crazy. This isn't even a jump of 1 on the Richter scale, yet it's nearly 8 times larger of an earthquake. It would cause 8 times as much damage theoretically, right? Wild, crazy. For reference, I think the largest earthquake in Spokane is like in the 5s. I think it's like 5.2 or something. The largest earthquake that's measured, which is like probably 8 or even less times the one in California. So it's pretty small. We don't really get earthquakes here. However, in the US, there is a place that gets a lot of earthquakes, more than California, in fact, and it's Alaska. Okay, Alaska is home to the largest earthquakes in history in the United States. In fact, it's home to the first, second, third, and maybe even fourth highest earthquakes. But what I want to do here is compare the second largest earthquake and the highest or the largest earthquake of all time. Both happened in Alaska, and both happened in 1 year span, right? So the second largest earthquake in Alaska, or in the United States, happened in Alaska in 1965. It had a magnitude of 8.7, which means that is equal to log base 10 of I over 0.0001, okay? We want to find the intensity of this because they're asking, or I'm asking, that the largest earthquake ever recorded was 8 times larger than this, and it happened the year previous, okay? So we need to find the magnitude of the largest earthquake of all time in the United States. 8 times larger than this one, okay? That's like this gap. Here we go. So first, let's solve for I in this case, and we're going to do the same thing. So I'm kind of just going to shortcut this. I know that I is going to be equal to 0.001 times 10 to the 8.7, right? Same process as what's happening in the one above. And so I can just type that into a calculator now. So we get 0.0001 times 10 to the 8.7 is an intensity of 50,118.27 centimeters, or 72 centimeters. Geez, that's like, what, 20 times larger, 25 times larger than this one? I don't know if I'm making that up. Divided by 12, 58. 30, 40 times larger than that one. Whoa, what am I doing? Jesus. I mean, geez. Anyway, I equals 5118.72. Let me rewrite that nicer. I need better handwriting. 5118.72. Okay. I know that the largest one, however, was 8 times larger than this, which means in the largest, the first place earthquake had an intensity I of 8 times 5118.72. And so I'm going to multiply this times 8, which means that the intensity of the largest earthquake, geez Louise, was 400,000 centimeters. 0.7879. Okay. So I'm rounding to the nearest second place, right? That's like, what? That's like hundreds of feet that the earth was moved. That's crazy. That's like insane amounts. I don't think it was any place that civilization was near, especially in Alaska in the early 60s. I don't even know. When was it even a state at that point? I don't remember. But still, crazy. All right, so what we want to find is the magnitude of this earthquake with this intensity. And so I know that the magnitude m is going to be equal to log of this giant number, 0.79 divided by 0.0001. And we're going to type that into the calculator. So log of 400,949.79 divided by 0.001001 is a 9.6 earthquake. Wow, 9.6 magnitude earthquake. Now, I have a little bit of a confession to make. The actual magnitude is not 9.6 because it's not exactly 8 times larger. It's like 7.93 times larger. I just wanted a nice number for the problem. And so the actual largest earthquake in the United States is 9.2 if you look it up. And that's why it's because it's not actually 8 times larger, but I just made it up for the problem. But either way, it's still very similar. Well, not very similar, but similar-ish enough, right? All right, so there's the whole packet, or the whole page, I guess, front and back of logs. And it's using log rules, solving logs. You can use this as notes on the test, as well as I highly recommend having your log and exponent rule sheet to help you on the test, okay? If you need help with the calculator, let me know. If you want to use Desmos, I can also help you with that to plug in values for log. But otherwise, good luck, have fun, and see you soon.